Hello everyone, welcome to the machine learning course. Please get ready. We are about to officially start our class, and I hope you all can gain something. Welcome back to our machine learning class. In this class,
we've gone a step further to broaden
our understanding of the k-means algorithm. We are going to understand the pros and cons of the k-means
algorithms, its applications in the taste of big data, how to determine the value of parameter k,
evaluation metrics for the k-means algorithm, and how to implement the k-means algorithm
in the Sakana library.
Here are the advantages of the k-means algorithm.
First, the algorithm is simple and fast, making it computationally efficient. It can handle large data sets, since its time complexity is approximately 2O, where the k is usually much smaller than the total number of data points, n. However, it's worth noting that the algorithm may converge to a local optimum rather than the global optimum.
K-means aims to minimize the squared error function
by finding k partitions. It works well when clusters are dense, spherical, or well separated, and when there is a clear distinction between clusters. Here are the shortcomings of the k-means algorithm.
The k-means algorithm
relies on calculating the mean of the clusters, which means it requires a definition of the mean. Consequently, it may not be suitable for certain applications
that involves categorical attribute
or non-numerical data. The user needs to provide the number of clusters k in advance, which can be challenging, especially when the optimal number of clusters is unknown or subjective. The algorithm is sensitive to the initial values of cluster centers. Different initial value can lead to different clustering results, potentially resulting suboptimal solutions.
K-means
is not well suited for identifying clustering with non-convex shapes of cluster that vary significantly in size. It assumes that the cluster are spherical and have a similar spread. The algorithm is sensitive to noise and outliers data points. Outliers can significantly affect the positions of cluster centers and lead to suboptimal clustering results. If we have a large number of
data points and large values of k,
the MapReduce method can be applied. Basic idea is to break down the representative steps into mapped function. Here's how it works. First, in the map function, we calculate the distance from each object in center points. We then select the closest center points for each object and output in pair in the form of center points and the objects. The reduce function takes these pairs and calculates the mean distance of the object in each cluster. These k-means are then used as the initial center points for the next round of clustering. By dividing the computations into the map and reduce functions, the MapReduce method allows for parallel preprocessing and the efficiently handling of the large datasets and high number of categories. When the value of k cannot be determined in advance, there are methods to help address this challenge. Two commonly used indicators are the sum of squares within a cluster and the overall sum of squares. Here's how they can be utilized. The sum of square within the cluster indicator measures the total square distance between each data point and its corresponding cluster center. By calculating its value for different values of k, we can observe how the clustering error change. Generally, as k increase, the sum of squares within the cluster will increase. However, it may occasionally fluctuate instead of strictly increasing. The overall sum of squares indicator calculates the total square distance between each data point and the overall means of all data points. Similar to the previous indicator, the overall sum of square can provide insight into how will the cluster capture the variance in the data. Again, observing the change in the values for different k values can help determine the approximately number of clusters. By analyzing these indicators and their trends, such as plotting them on the graph, we can look for an able point where the rates of decrease in the sum of squared within the cluster or overall sum of squares slows down significantly. These elbows points can indicate the suitable values of k. That strikes a balance between capturing meaningful clusters and the minimize clustering errors. So, when the k value cannot be determined beforehand, we can leverage these indicators to access different values of k and select the most appropriate one based on the observed trends in the sum of squares within the cluster and overall sum of squares. The sum of square errors in cluster is not only influenced by the number of centroids, but also by the factors such as the size of the datasets and dimensionalities of the data and the volume of the data. Generally, larger datasets tend to have a larger sum of square errors, and higher dimensional data also contribute to large errors compared to a lower dimensional data, even with the same number of centroids. When the data volume is larger, there is more information to be clustered, and the sum of square errors tend to be increased. Similarly, when dealing with high-dimensional data, the presence of additional dimensions can result in more variation and potentially larger errors in clustering process. It's important to consider the impact of data volume and dimensionalities on the sum of square errors when evaluating the qualities of clustering results and selecting
appropriate numbers of centroids.
Here we list several metrics for calculating the clustering qualities for the
k-means algorithms.
You can utilize the corresponding functions within Scikit-learn to perform the calculations. We're providing everyone with a small example along with its corresponding codes. It reads data from a file performing k-means clustering using the scikit-learn library and visualizes cluster along with their centroids using matplotlib. You can run these codes step by step in the Jupyter Notebook on your own to have a further understanding of the algorithm. So, to sum up, in this class, our main focus was to provide an understanding of the advantages
and disadvantages of the k-means algorithm,
its applications in parallel computing contexts, and the selections of k-parameters, evaluation metrics for accessing the algorithm's performance, and examples of its implications.
In the scikit-learn library,
We aim to ensure that everyone gains a reasonable understanding
of the k-means algorithm,
which is classical clustering method, by discussing its strengths, limitations, and various aspects of its practical usage. We hope to have provide
a comprehensive overview of k-means.
So, thank you for joining this class, and we hope that you
Now have a solid grasp of the fundamentals of the k-means
algorithm.